Welcome, fellow investigators, to the deep dive. Today, we are embarking on a high-stakes mission, hunting for meaningful patterns hidden within vast oceans of raw data. Our target is nothing less than the very mechanism that allows computers to see the world, a technology known as Convolutional Neural Networks, or CNNs. Imagine staring into a chaotic sea of pixels. To the untrained eye, it's just noise, but beneath the surface lie fundamental structures, waiting to be uncovered. Our challenge is to build a systematic approach, a neural network, capable of navigating this digital deluge. We need a system sophisticated enough to look at millions of data points, the colors, the intensities, the coordinates, and somehow deduce that what it's observing is, in fact, a car or a cat or a supernova. CNN provide the blueprint for this investigation. They are designed to break down perception into manageable, sequential steps, starting with the most basic elements and combining them into complex, abstract concepts. Over the next few minutes, we will unpack the tools and techniques used in this hunt, from simple filters to hierarchical feature assembly, revealing how we introduce intelligence into the machine. Get ready to dive deep into the math and mystery behind artificial vision. To begin our investigation, we must first understand the raw data we are dealing with. For humans, looking at this image of a car is immediate. We instantly process its shape, function, and context. But a computer doesn't see a sleek automobile. It sees a 3D tensor, a massive, organized grid of numbers. Think of the image as having 3 dimensions: height, width, and depth. The height and width correspond to the pixel grid we are familiar with. The depth, however, represents the color channels: red, green, and blue. For every single pixel in that grid, the computer stores 3 numerical values, ranging typically from 0 to 255, quantifying the intensity of each primary color. If we have a high-resolution image, this grid can contain millions or even billions of these 3-dimensional vectors. The elegant car we recognize is entirely lost in this immense numerical ocean. Our central challenge is therefore existential. How do we build a system that can navigate this deep numerical sea and identify the distinct object, the pattern, hidden within these overwhelming data points? We need to go beyond simply cataloging numbers. We need a method to extract meaning and structure from sheer numerical volume. This is where our investigative tools come into play. We can't expect to find the whole car immediately. Like any good investigation, we must start by searching for the simplest, most fundamental clues. This means hunting for basic patterns, such as vertical edges, slight curves, or color gradients. Our primary investigative tool for this task is the filter, also commonly referred to as the kernel. As shown here, a kernel is simply a small matrix of numerical weights. These weights are specifically chosen to represent a simple pattern. In this example, our kernel is designed to respond strongly to a specific vertical edge. The central mathematical operation that brings this filter to life is called convolution. Convolution works by sliding this filter, our pattern template, over every possible section of the input image grid. At each location, we perform a weighted sum. We multiply each pixel value currently covered by the filter by the corresponding weight in the filter, and then sum up all those products. The result of this calculation is a single output value. If the underlying image pixels happen to match the filter's pattern, that is, if it finds the specific edge it's looking for, the output value will be exceptionally high. This high output is like a sonar ping or a perfect match signal, telling us exactly where that specific simple pattern exists in the image. This resulting map of high and low values is what we call the feature map, marking the success of our initial, localized hunt. A real investigation rarely relies on a single specialist. Likewise, a single convolutional layer deploys not one, but a whole fleet of specialized probes, or filters, simultaneously. We might deploy hundreds of these filters, each trained to find a different, simple pattern. One for vertical edges, one for horizontal edges, one for diagonal lines, and perhaps several to detect specific subtle color curves or texture variations. Critically, each filter sweeps over the input image completely and independently of the others. The process is massively parallel. Because each filter is looking for a unique pattern, it produces its own dedicated map of findings. This output map for a single filter is what we call a feature map. The vertical edge specialist, for example, will produce a feature map that brightly highlights every vertical line segment it detected in the original input image. So, if the input image is fed into a convolutional layer containing 64 different filters, the output is not a single map, but a stack of 64 feature maps. Collectively, these feature maps represent a comprehensive, localized fingerprint of the input image, detailing exactly where all the fundamental building blocks, the edges, curves, and gradients, are located. This array of maps is the foundation upon which the network builds increasingly complex understanding. As effective as our filters are at detecting patterns, we immediately run into a critical flaw inherent in this pixel-perfect approach. The target is elusive. Our filters are too sensitive to the exact spatial location of a pattern, a vulnerability known as a lack of translational invariance. Consider this example. If we have a filter specifically designed to detect a corner in a precise 3x3 pixel arrangement, what we call the perfect alignment, it yields a 100% match, a very strong signal. But what happens if that feature, say the corner of a car window, shifts just one single pixel to the right or down? This minor spatial displacement, the one pixel shift, can dramatically reduce the correlation score, perhaps dropping it to a mere 20% or even causing the filter to miss the feature entirely. In the real world, objects are never perfectly aligned. A car window corner might be detected at coordinate 100, 150 in one photo and 101, 150 in another, due to slight camera shake or object movement. We need our system to recognize that a feature is present, regardless of this minute shift in position. This pixel-perfect rigidity is a major weakness that must be overcome if our hunting system is to be robust and successful in identifying objects in the wild. The solution to overcoming the flaw of pixel-perfect rigidity lies in switching from a point-based search to a regional search. We must introduce resilience against small spatial shifts, a property known as translational invariance. The tool we use for this is pooling, specifically max pooling. Instead of asking, "Is the corner present at this exact pixel coordinate?" we shift our question to, "Is the corner present anywhere within this small 2x2 region?" The max pooling operation works by sliding a small window, often 2x2 pixels, across the feature map we just created. For every region the window covers, we retain only the strongest signal, the maximum value found within that 2x2 square. This maximum value represents the most confident detection of the feature within that local area. By keeping only the maximum, we effectively discard the exact coordinate information, meaning that if the feature shifts by 1 pixel, the maximum value often remains the same, thus achieving invariance. This operation serves two vital purposes. First, it makes our detection robust, ignoring small shifts in position. Second, it downsamples the feature map. A 4x4 map becomes a 2x2 map, making the subsequent steps of the investigation smaller, faster, and computationally more efficient, all while retaining the most critical information extracted by the filters. While pooling is highly effective at introducing resilience and downsampling our data, it constitutes a separate step performed after the convolution operation. In our relentless pursuit of efficiency, we can integrate this downsampling effect directly into the convolution step itself using a technique called striding. Striding simply means taking bigger steps with our filter as it sweeps across the input image. In a standard convolution, we use a stride of 1, meaning the filter moves just 1 pixel at a time, resulting in a large output map that retains the full spatial resolution of the input. For an 8x8 input with a 3x3 filter, this results in a 6x6 output map, requiring 36 calculations. However, if we introduce a strided convolution with a stride of 2, we instruct the filter to skip every other pixel, effectively moving 2 pixels at a time. This drastic reduction in overlap means the filter evaluates far fewer positions on the input. As a consequence, it naturally produces a significantly smaller output map. In our example, a stride of 2 immediately reduces the 6x6 output map to a 3x3 output map, requiring only 9 calculations. This is a much faster, more efficient way to cover the vast ocean of data and integrate the benefits of downsampling without the overhead of a separate pooling layer. Now we arrive at the core of the investigation, assembling these preliminary clues into sophisticated concepts. The power of the convolutional neural network lies in its hierarchical structure. Layer 1, as we've discussed, contains filters that look only at the raw input pixels and find simple features, like vertical edges, horizontal edges, and basic curves. The crucial insight is what happens next. The filters in Layer 2 do not look at the original image. Instead, they look for patterns within the feature maps created by Layer 1. They are trained to combine the simple feature outputs. For example, a Layer 2 filter might see two parallel vertical edges combined with a horizontal line and deduce that this arrangement forms a component shape, like a rectangle or a circle. This process of abstraction repeats. Layer 3 filters then look at the component shape feature maps from Layer 2. They might see a circle combined with a wedge shape and identify a high-level feature, such as a tire, or see a rectangle and identify a window. This repetition builds a powerful hierarchy of abstraction. Each successive layer takes increasingly complex, abstract concepts from the previous layer, gradually transforming the raw pixel data into a complete, conceptual profile of the object. The tire, the window, the grille, all in their correct spatial relationship. This layered transformation is what makes the final classification possible. The moment of truth, the reveal, is achieved by assembling the final profile. After the raw pixel data has journeyed through multiple sequential layers of convolution and pooling, it has been completely transformed into a rich, abstract set of features. We've moved from simple edges to component shapes, and finally to object parts like tires, headlights, and body contours. These abstract feature profiles are then passed to the final stages of the network, typically a standard fully connected layer. This layer takes the complete evidence profile, the knowledge that a tire, two windows, and a specific car body shape are present in the correct spatial configuration, and uses this information to make the final classification decision. This final stage is no longer concerned with where the pixels are, but rather with the probability of the collected features belonging to a known category. If the assembled evidence profile aligns strongly with the known profile of a car, the network provides its classification, car, along with a confidence score. In this example, the high confidence score of 99.2% indicates that the mystery is solved, the object has been successfully identified, and the hunt is complete. This culmination is the goal of the entire CNN architecture. In any specialized field, mastery requires advanced tools, and CNNs are no exception. Our investigators' toolkit includes several advanced methods used to refine the convolution process. Two crucial techniques are padding and 1x1 convolutions. First, consider padding. When we apply a filter near the edge of an image, its footprint often hangs off the edge, meaning we can't perform the computation correctly. This not only results in lost information at the boundaries, but also causes the output map to shrink slightly with every convolution, which can be problematic for maintaining layer consistency. Padding solves this. It involves adding a border of zeros, or padding, around the entire input image. This ensures that the filter can be perfectly centered on every single element, even those at the original edges. Padding prevents information loss and helps us control the spatial size of the output feature maps. Second, we have X convolutions. This is a surprisingly clever technique using a filter footprint of just 1 pixel by 1 pixel. Since the filter is so tiny, it doesn't look for spatial patterns like edges or curves. Instead, it operates exclusively through the depth of the channels, the stack of feature maps. If we have 12 input feature maps, the 1x1 convolution acts as a linear combination across those 12 channels for every pixel position. This technique is incredibly powerful for reducing the number of feature maps, effectively compressing information, and reducing the dimensionality of the depth, while making the network significantly more efficient without sacrificing the spatial resolution of the image. With all the individual tools defined, we can now visualize the complete anatomy of a pattern hunter. A typical convolutional neural network architecture is a highly structured sequence of stages that progressively transforms the raw input data. It begins with the input image, which is immediately represented as the input data tensor. For a standard image, this might be 224 x 224 pixels with 3 color channels. The data then enters the first major stage, a combination of convolution followed by pooling, denoted as conv plus pool. The convolution increases the number of feature maps, the depth, as the filters extract simple features, while the pooling step halves the spatial dimensions, height and width, to introduce robustness and efficiency. This pattern repeats. We move into the second conv plus pool block, where the spatial dimensions are halved again, e.g., from 112x112 down to 56x56, and the depth, representing the complexity of the extracted features, is usually doubled. This progressive transformation, decreasing spatial size while increasing the depth of abstract features, continues through the architecture. Finally, the highly abstract, deep feature map is flattened into a 1D vector and passed to the fully connected layer. This final section performs the high-level reasoning and culminates in the output classification, providing the probabilities for potential objects, completing the blueprint of our sophisticated pattern hunter. The hunting process we've discussed, transforming an image into abstract concepts, is essential for classification. But what if we want to run the hunt in reverse? What if we have an abstract concept of a car and want to generate a photorealistic image of it? The tool for this generative task is transposed convolution, also sometimes called deconvolution or fractional strided convolution. Transposed convolution is the mathematical reverse of a standard convolution. Instead of downsampling and reducing feature maps, it learns how to upsize or upsample the input, turning a small, abstract feature map into a much larger, more detailed image. It takes a high-level concept, represented by a small grid of abstract features, and spreads that information out, mapping it onto a larger grid and filling in the necessary detail. Imagine starting with a conceptual profile, like the components of a car, and using the transposed filter to project those concepts onto a larger canvas, carefully filling in the textures of the tire treads, the curvature of the windshield, and the precise color gradients. This technique is fundamental to modern generative models, such as those used in image synthesis and style transfer, allowing AI to move beyond merely recognizing the world to actively creating it. Perhaps the most powerful and initially unsettling part of this entire story is that we, the engineers, did not manually handcraft the thousands of filter weights used in the deep layers. The network learns them entirely on its own. The hunter trains itself to see. When a convolutional neural network is first initialized, the filters in every layer are simply random, meaningless numbers, as shown in the before training state. The network has no idea what an edge or a curve looks like. The training process involves showing the network millions of labeled images, a car, a tree, a dog, and asking it to classify them. Initially, its guesses are terrible. But here's the magic. After every incorrect guess, the network employs a sophisticated process called backpropagation. This mathematical feedback loop adjusts every single weight in every filter across all layers, slightly correcting them to reduce the error. Over countless iterations, this repeated correction teaches the network which patterns matter. Through this relentless self-correction, the random filters slowly evolve into highly specialized feature detectors. As seen in the after-training state, the filters learn to specifically recognize sharp edges, smooth gradients, and complex curves. This self-learning mechanism transforms a random numerical matrix into a specialized visual intelligence, allowing the hunter to truly understand the structure of the world it observes. Let's recap the depths we've charted and assemble the complete investigative process of the convolutional neural network, condensing it into 5 key stages. 1. The starting point. We began in a vast sea of pixels, a 3D tensor of numbers where the hidden object, the car, was completely imperceptible to a standard algorithm. 2. The discovery phase, convolution. We deployed specialized filters, or kernels, using the mathematical operation of convolution. These filters act as sonar pings, efficiently sweeping the image to find simple, fundamental clues like edges and curves, resulting in a feature map. 3. The resilience phase, pooling and striding. Recognizing the flaw of pixel-perfect rigidity, we introduced pooling and striding. These techniques allowed for a more robust, regional view, making our detection system resilient to small shifts in position while simultaneously downsampling the data for efficiency. 4. The abstraction phase, hierarchical layers. Multiple layers of convolution are stacked. The network progressively assembles those simple clues into more complex concepts, moving from edges to component shapes, and finally to high-level object parts like tires and windows, building a complete, highly abstract profile of the target. 5. The conclusion, the reveal. Finally, the network utilizes this rich, abstract profile to make its final, high-confidence classification, successfully identifying the object and solving the visual mystery. We conclude our deep dive into convolutional neural networks. The ocean of data is full of patterns, and now you know how to hunt. While we have focused our discussion primarily on image recognition, the fundamental principles of CNNs, the idea of using localized filters to extract hierarchical features, and the use of pooling to achieve translational invariance are universally applicable. These techniques allow us to find structure and meaning not just in pictures, but in any form of organized data. Whether you are analyzing the spectral signatures of distant planets, classifying the morphology of cells, parsing the complex patterns in audio waveforms, or discovering features in raw 1D time series data, the CNN architecture provides a powerful, scalable framework for pattern detection. From the depths of raw pixel values, we have successfully charted a course toward abstraction and intelligence. This methodology is transforming science, engineering, and technology, proving that with the right tools, no pattern is too subtle and no dataset is too vast. Thank you for joining the deep dive. The hunt continues.